There you have it. Welcome again to another episode of Chem in 3. We began today's episode with students in my class building this molecule, CH3OH, methanol. They had the entire molecule broken into its components of bonds and atoms, and they were blindfolded, and then they had to try to put together the structure. Once they finished putting the structure together, we reflected on how this relates to this equation, the Arrhenius equation, which considers some of the factors that affect the rate of a chemical reaction, including the activation energy, the temperature, and whether or not the reacting particles have the right orientation, and how many of those collisions between one reacting particle and the next are of the right orientation to cross the activation energy barrier for a reaction. Like this activation energy barrier here, as reactants cross this barrier and become products. But if we were to relate this to our model, then the amount of energy that the students needed to put the bond together, and as you notice, a couple of them were actually struggling to snap the bonds into place. They only had a certain amount of energy to offer. And if that amount of energy that they could offer was not enough to snap the bonds into place like this, then it provides a good analogy to understand that even though some reacting particles have the right orientation and they collide in the right way, they may not have the kinetic energy required to cross the activation energy barrier. And one way to increase this amount of energy is to increase the temperature. Recall from the Boltzmann distribution curve, where you have T2 being higher than T1, there are more particles that have the kinetic energy to cross this activation energy barrier. Temperature is one factor that affects whether or not a reaction can occur. The blindfolded students had to ensure that the energy that they were putting in to snap bonds together was put in with everything lined up correctly, like this bond fitting in like this. They had to ensure that the steric factor was taken care of. And the Arrhenius equation brings together temperature, activation energy, and the collision and the steric factor are joined together in this entity called the pre-exponential factor. And this pre-exponential factor is multiplied by the exponential factor, which is the base of natural logs 2.718, and then this is raised to the power of the negative activation energy divided by the gas constant multiplied by temperature. So then you might wonder, what is the point of including the gas constant? So let's move in then and take a closer look at the Arrhenius equation and how it includes three main factors that affect K, the rate constant for a chemical reaction.
And here we can see the factors that affect the rate of a reaction. K, the rate constant, is affected by the activation energy barrier that the reactants must cross to go from reactants to products. In order to cross this activation energy barrier, the reacting particles must have the right amount of kinetic energy, which comes from temperature, and they must be oriented in the right way so that they can come together. The steric and collision factors, these two parameters, go into producing A, the pre-exponential factor. Then we have E, the exponential factor, the base of the natural log, and then the two other factors, the activation energy and the temperature. The gas constant is included in this expression, and when it is, these units all cancel to make this part of the equation a unitless parameter. So let's say then, for a first order reaction with units of seconds to the -1, then the units of K would be the same as the units of A, the pre-exponential factor. In our next episode of Chem in 3, we will look at how to relate the equation of a line y is equal to mx plus c to the Arrhenius equation.